Good day, guys. Welcome to Calcumind, and today we'll be looking at application of ordinary differential equation to a resistor and an inductor circuit. So this is basically a circuit which involves a resistor and an inductor connected in series, whereby this is the current source and this is the voltage source. So we are going to be showing how the resistor and the inductor, the current flows through them, whereby the resistor current is changing in it and also the inductor current is also changing in it. We are being presented with a question which states that an inductor of inductance 10 Henry and a resistor of resistance 15 ohms are connected in series to a 90-volt supply. Determine the values of the circuits I after 2 seconds. So we are going to be solving it. We are going to be modeling an equation whereby the resistor and the inductor are present in series. So using the Kirchhoff's voltage law, whereby KVL, whereby the resistor, the voltage drop in the resistance V, let's call it V, is equal to VR. The voltage drop in the resistor VR is equal to IR. And the voltage drop in the inductor VL is equal to L di over dt. So we can note that for the inductor, the current is changing with respect to time. It's oscillating with respect to time. So now we are going to be summing them up. The voltage source V is equal to VR plus VL. And now we have gotten our voltage source to be E. So we are going to impute that into the equation. So E is equal to IR plus L di plus dt. So now we are basically forming the equation. So we are going to be dividing through by L. So let's divide by L. So this will be E divided by L is equal to R over L I plus L over L di over dt. So now we have gotten this. You can see that this is looking like an ordinary differential equation already. We are having the I over dt, we're having R over L, we're also having E over L. So now let's cancel out. BL cancels out this. So now we'll be having E of L is equal to R over L plus di dt. So now let's restructure this, taking this over to this side, taking this over to this side. So we'll be having di over dt plus R over L is equal to E of L. To solve this question, we can see now that we have the I on this side, dt, we have R over L and E over L. So now we are going to be using the integrating factor method. If you watch our videos on integrating factor, this will be a breeze through for you. But if you haven't watched our previous videos on integrating factor, you can go back and take a look at the playlist to get a better understanding. So now, using the integrating factor method, so using the integrating factor method is basically comparing this equation that we have gotten over here to a standard equation which states that di over dt plus p with respect to the function I t is equal to this is p with respect to the function t, whereby I is present here, this I, then Q of t. So now, looking at this equation, they are both similar. This is P of t, this is Q of t. So now, P of t, let's write it out. P of t These are the focal points. P of t, Q of t, and I of f are the focal point for integrating factor method. We are going to be using the formula integrating factor method. So P of t now is R over L, and Q of t is E over L. So now we are going to be substituting it into the equation, which says that let's write using the integrating factor method. So the method states that I, which is the current in the circuit, is equal to 1 over the integrating factor, I of, since we are differentiating with respect to t, is I of t, all in brackets, integral of I of t, Q of t. So now this is the formula. We will now be finding I of t using this parameter. So I of t now is another formula. I of t is a standard. I of t is equal to E integral of P of t dt. So we are basically integrating it with respect to an exponent. So now we have gotten our P of t. We are going to be substituting it back into this place. So this E is equal to R over L dt. So now this might look confusing for a start. How are we going to be integrating R over L with respect to an exponent? It's looking challenging, it's looking complex. But now, if you have something like integral of 4 over t, if you have something like the integral of 4, you just basically add t to it. So the integral of 4 is 4t. So now we are going to be just using the same idea. We have RL, we are asked to integrate it. We basically add RT, add t to it. So I of t, let's not confuse it, let's just add an f so we can differentiate our integrating factor and our current. So let's call this I of f. Call this I of f, and also call this I of f. So we don't confuse our current, which is this small with an I, with the integrating factor. So I of f now is equal to E R over L divided by T. So now we are going to be imputing all the parameters. And let's not forget I omitted a dt here. So we are going to be multiplying this with respect to dt. So now let's impute all the parameters. We have I of t. So this is 1 over e raised to the power r l t integral of e raised to the power r l t. Our q of t is giving us e raised to the power e divided by l dt. So now we are going to be integrating this function, and as we can see, E over L is constant. The voltage in the circuit, the whole voltage from the diagram we represented before, E was constant and L was constant. I think it was a 10. So those values are constant, and anything that is a constant, we take it out of the integrating sign. So now we're going to be doing also 1 over 1 divided by a value. So this 1 over a is the same thing as a raised to the power minus 1. So now we are going to be illustrating this. This will be E minus R LT. So since we are taking this up, we are going to be adding a minus to it. So now this, taking this out, E over L, integral of E R L T dt. So now let's work this out. If you differentiate this, integrate rather with respect to t, this value is going to be taken down. So now if you have something like e raised to the power 4t, you're being taxed to integrate this. What you simply do is taking this 4 and dividing it all through. So this e raised to the power 40, the integrating e raised to the power 40, if you integrate it, you get e raised to the power 40 divided by 4. So that is the same idea you'll be pushing through with this. So this e minus r l t, this e over l, integral of, okay, let's just write it out. So this e r l all divided by r over l. Let's write it out clearly here. So this e I is equal to e raised to the power minus r l over t, all in brackets e over l. Is equal to e r l t all divided by l over r. Okay, r over l is r over l plus c. So this is the idea now we are going to be working with. We have added our integrating constant. So now this e over l, r over l, they are going to be cancelling out, whereby if you're dividing through, the value at the denominator is going to flip. So now this will be I is equal to e minus rl t e over l. So now once we want to multiply, this l is going to come up. So this times l over r e r l t plus c. So now we can see everything clearly. This cancels out this. We'll be left with I is equal to e minus rl over t e over r e rl t plus c. So this cancels out this, then e divided by r, multiplying this plus c. So now using the laws of integration, laws of indices rather, this will cancel out this since both of them have the same base. So this will be e a multiplied by eb is the same thing as e a plus b. So now this minus rl over t plus rl over t will give us 0. It's basically cancelling it out. So this I is equal to e over r minus r over lt plus r over lt plus c. This is in brackets plus c. Then this will also multiply this. So this e minus rl over t. So now we get the idea now. This will cancel out this. It will be 0. So this I is equal to e over r e raised to the power 0 plus c e minus r l over t. You're getting the idea now. So e raised to the power 0 is 1. So we'll be left with I is equal to e over r plus c e raised to the power. So now this is the model equation that we have talked about, deriving through from the voltage division, the voltage drop in the resistance, and also the voltage drop in the inductance. We sum them up using Kirchhoff's voltage law and using the integration factor method to break it down and getting the current to also solve the differential equation And we are now coming to this point whereby the current is equal to the voltage divided by the resistance plus the integrating constant multiplied by the exponent raised to power Rm multiplied by T. So this is the model equation. And lastly, we'll be finding the constant. So now, using the boundary conditions, we'll be able to find the constant, whereby I is equal to 0 and T equals to 0. These are basically the starting, when the time was 0, the current was 0. So that is the idea we are working with. Let's call them boundary conditions. So now, we are going to be substituting the value. So this 0 is equal to E over R plus E minus R over L, 0, all multiplied by C. So now, this is going to cancel out. Minus R over L multiplied by 0 is going to be giving us a 0. So this 0 is equal to E over R plus E raised to power 0, all multiplied by C. So now, E raised to power 0 is 1. So this is 0 is equal to E minus R plus 1 multiplied by C. So now, from this equation, we're making E divided by R the subject of the formula by basically taking it over to the left-hand side. So let's do that. So this minus E over R is equal to 1 per C. So this C is this 1 multiplied by C is the same thing as C is equal to minus E over R. So now we have gotten our C from the equation. We'll simply multiply it, we'll simply substitute it back into this equation. So let's call this equation asterisk. So now we'll substitute C into equation asterisk. So now this I is equals to E over R plus E minus R LT minus E over R. So now we are going to be simplifying this further and taking out the common parameters. You can see E over R is common here. We can also see E over R is common here. So now let's do this properly. So this I is equal to E over R. So taking this out, we have 1. Taking this out from also here, we can see that there is a minus here. So this minus E raised to power minus R L T. So now this is the complete modeled equation, whereby we have also found the constant C. So now, from the question they gave us, they say we should determine the value of what?
The circuit I after 2 seconds.
It's okay. So they say the value I, we don't know the value, at t equals to 2 seconds. So we have simply converted the word problem into this simple statement. So now, at t equals to 2 seconds, we'll simply get our value of I using this equation. So let's do that. Substituting t equals to 2 seconds, I from the equation they gave us E as what?
They're giving E raised to power minus 3 is equal to 0.05.
No, E, 90 volts, the voltage in the circuit.
90 volts.
Okay, so now E is equals to 90 volts. Let's write out all our parameters. E is equals to 90 volts. R is what?
15 volts.
L is what? 10 Henry, right?
Yes, 10 Henry.
Okay, and T is equals to 2 seconds. So I is equal to 90 divided by R, which is 15, 1 minus E minus R, which is 15 also, divided by L, which is 10, multiplied by T, which is 2. So now let's simplify this. This I is equal to 6, 1 minus e raised to power minus 15. There is 3 over 2 multiplied by 2. So these 2 will cancel these 2. So this I is equals to 6, 1 minus e raised to power minus 3. And from our equation, from the question, we are given that e raised to power minus 3 is what?
0.05.
So this 6, 1 minus 0.05. So 1 minus 0.05 is 0.95. So this 6 multiplied by 0.95, giving what?
5.7.
5.7. So now I, at 2 seconds, is equal to 5.7 amps. So now we have gotten our modeled equation, which is this. We have also got, our modeled equation, which is this. We have also gotten the time. We have gotten the current at t equals to 2 seconds, which is 5.7 amps. So that is we come to the conclusion of this video. Anywhere you don't understand any problem, you can leave it down in the comment section. Thank you for watching the video, and make sure to like, share to your friends that have issues of application of ODE with respect to RL circuits. Thank you for watching the video once again.